Okay, this is part 2 of the chapter 14 lecture tutorial. We'll pick up with discussing icebox problems, and what an icebox is simply an acronym, ICE, that stands for initial concentration, C for change of concentration, and of course E for equilibrium concentration. And the box simply refers to a table that we will be setting our problem up in, so that's icebox. And we're just going to introduce the icebox method in this chapter. We're not going to get too detailed into our discussion, but it's very imperative that we get a good grasp on the concept, because we'll be using it heavily in the next couple of chapters. So essentially what we're trying to do is determine what the initial concentration is, and then know the change, and therefore be able to determine what the equilibrium concentration is going to be towards the end of the reaction. And the way we do that is, of course, by setting up our table. So some guidelines here as to how we will proceed. The first thing is that we'll express the equilibrium concentrations of all the species in terms of the initial concentration. So we'll always know the initial concentrations, or the I values. And then we'll determine what the change is, and that change will be, of course, a single unknown value of x, okay, and that will represent the change in our concentration. So the change is always going to be an x value, minus x, of course, for the reactants, and plus x for the products, because as we convert our reactants, their concentrations will decrease, and as we convert them into products, the product concentration will increase. So again, the equilibrium constant expression will be based on those, and then the change is going to be what we calculate. So once we have our initial concentrations and the change set up, we'll know what the equilibrium value is going to be. It'll be the initial minus x for the reactants and the initial plus x for the products. How do we solve, of course, for this change? Because if we don't solve for x, we won't know what the final equilibrium value is going to be. Well, we'll solve for x using the equilibrium constant expression. So we will, of course, write the expression for K, products over reactants, and finally, step 3, we'll solve for X in the species. Again, that's going to be a lot more important in the coming chapters, but you do have slide number 20, which is a very good example, but more in-depth problems will happen in chapters 15 and 16. Just a quick example of an icebox problem here. No K expression necessary, but just to give you an idea as to what an icebox will look like and the general principle behind it. Here we have A plus B, which gives us C, and of course it's ICE, icebox. Initially we had 2 molar of A, 1.5 molar of B, and 0 of C. Again, usually we have some of the reactants and none of the product. And we will write the change in terms of minus x for the 2 reactants and plus x for the product. At the end, we don't know what the equilibrium is, but we do know that it's 2 minus whatever x is, and that's what we have left at equilibrium. So 2.0 minus x technically is equilibrium. And for B, it's 1.5 minus x is equilibrium. And for C, 0 plus x is 1.0 at equilibrium. So we would solve for x. Well, given that we know that we lost reactant amounts, and that's a minus, we know that 2 became 1 by losing 1. So x must be equal to 1. 2 minus x equals 1, x is equal to 1. And x should be, of course, the same value throughout. Again, with B, 1.5 minus x is 0.5 at equilibrium. So again, what was x? 1.0. And then finally, we gained the product, so it's 0 plus x, and of course we know that x here is the unknown, quote unquote, which equals 1.0, and we know x is 1.0. So you could think of this in terms of calculating the unknown based on knowing what the initial concentration is and perhaps what the equilibrium is. It won't be as straightforward, obviously, in our problems, but this gives you a general idea that where the x tells us the change in concentration, and by knowing the initial and equilibrium, that will help us to determine future calculations and concentrations for the same reaction if we used different concentrations. So It obviously won't be as simple as just knowing or having values like this and just subtracting or adding and determining the value of x, but it gives us a good idea as to what an icebox scenario would look like. The next topic that I want to discuss is the Le Chatelier's principle. It's the last topic here in chapter 14 and a very important one. Le Chatelier's principle, let's start off by just understanding and defining what it is. Le Chatelier's principle states that if you apply an external stress to a system that is already at equilibrium, that means you're basically disturbing the equilibrium. So the system will make an adjustment. It will adjust itself in such a way to basically partially offset that stress or reverse it and restore itself to equilibrium. If you think about it, it's when you hit the brakes on your car and you lurch forward. Of course, first you go forward and then you go back once you've come to a full stop. And it's almost like for every action there is an equal and opposite reaction. That's kind of a similar principle in that, yes, if you disturb the system in one way, the system will reverse what you've done so that it can offset that disturbance and go back to what it was before it all happened. So basically it's trying to restore its equilibrium position. So there are different ways that you could offset or disturb the system at equilibrium. Certain things that you could do. First and foremost, you could increase concentrations of your reactants or products. This would, again, cause a disturbance. So you could add a reactant or product. You could remove a reactant or product. So that means you could increase a concentration or decrease a concentration. So there's one factor that could act as a stressor. Another stressor can be in terms of volume, temperature, and so on. So we'll discuss other properties that are studied by Le Chatelier's principle. But before we get a little ahead of ourselves, let's again discuss this disturbance and how we try to reverse it. For example, if you add a reactant and therefore increase its concentration, the reaction will shift in such a position to decrease the concentration back to what it was. Because you increased it, the reaction will try to decrease it. How so? It will shift the equilibrium to a position where it will try to consume that reactant. Okay? You can't just get rid of it, but you can consume it. Again, that would mean shifting to the right or to the left, whichever direction in the reaction that would allow you to consume that particular reactant that you've added that's in excess. Let's say you removed a reactant or product. That means you're decreasing the concentration, so you would try to do the opposite, which would mean you would try to regenerate it or make some more. So you would shift the equilibrium in a way to regenerate that lost reactant or product and make up for what was lost. So let's take a look at some other factors that can be influenced or can act as stressors in reactions using Le Chatelier's principle. Number one is concentration, of course. You will shift to the side that will reverse the disturbance, meaning make more of what was taken out or use up what was added in. 2, volume. This again mainly affects gases as well as pressure. Volume. The lowest volume, okay, shifts to the side with the lowest number of moles. So if you lower the volume, let's just say lower, if you lower the volume, you'll shift the reaction to the side with the lowest number of moles. By the same token, pressure, again it affects gases. The higher the pressure, the more you're likely to shift to the side with the lowest number of moles. Notice here, volume and pressure are related for gases. This is Boyle's law from Chem 1. They are inversely proportional. So as you increase volume, you decrease pressure and vice versa. Notice that if you lower volume, you shift to the side with the lowest number of moles. A lower volume means you have higher pressure, which again would shift to the side with the lowest number of moles. So really 2 and 3 are the same principle if you think about it, because volume and pressure are related. Number 4, temperature. Temperature is another determinant and stressor that can affect or shift the equilibrium. And this, of course, depends on whether you are in endo or exothermic reaction. And 5 are catalysts. And catalysts do not shift the equilibrium at all. So these are different, you could say, these are different characteristics or properties that could potentially shift or affect an equilibrium reaction. Numbers 1 through 4 can, but number 5, catalysts, do not shift the equilibrium. They only help you get to equilibrium faster because that is the role of a catalyst. Okay, so let's there's a note here, of course, about the pressure and volume relationships that I had mentioned. A note here on temperature again. Please recall from Chem 1 that if a reaction is considered to be exothermic, then heat is actually considered to be a product. So you will actually see the energy values written in terms of products. And this is an example right here where you can see A plus B produces C plus D and 45 kilojoules of energy. Given that the 45 kilojoules of energy are in the product section, that means they are produced and released, making this particular example an exothermic reaction. Had this 45 kilojoules been written over here on the side of A and B, that would have meant that we have an endothermic reaction, because in an endothermic reaction, the energy or kilojoule value would be listed on the reactant side, because energy would actually be a reactant or a necessity in getting the reaction started. So again, you should know if something is exo or endothermic before you know which direction the equilibrium would be shifted. So let's take a look at this example and determine in which direction will the equilibrium be shifted under these 4 scenarios, these 4 conditions. A, let's say we added more of product C. We've added product C. So we're adding C, which means we're adding a product. So in turn, we need to use it up because we've added it, we've increased the concentration. The disturbance is an increase, so we need to find a way to decrease. You can't just stick your hand in there and take it out. So what do you have to do to decrease? You have to consume it. So we'll shift the equilibrium here to the left. And by shifting it to the left, we'll take C and D and make more A and B. In turn, using up the extra C that was added. So here we're going to shift to the left. All right, what if more of reactant A was added? Adding more of A. Adding more of A means I need to get rid of A. I need to convert A into something else. So I will shift it to the right and convert A into products. And by adding A and disturbing the equilibrium, I can offset that by shifting it to the right and converting A to C and D, and thereby decreasing the concentration. How about removal? Let's remove reactant B. If I take this out, that means I need to find a way to replace it. The only way to regenerate and replace the missing B that was caused by this disturbance is to take C and D, right, and go in the reverse direction and convert C and D into a little bit more of A and B. So again, in this case, we will shift it to the left. And last but not least, how about temperature? This is, of course, an exothermic reaction. We know that because the kilojoules of energy is a product. So let's see what happens when we increase the temperature. The temperature, what would happen here if the temperature was increased? Okay, well, that means we've just added more energy. The whole purpose of this exothermic reaction is to produce energy and get rid of it. That's why it has a negative delta H. We want to get rid of heat. By actually adding temperature, increasing the temperature and adding heat into the system, you're slowing this process down. So by adding heat, you're actually slowing this process down, adding more energy, in turn shifting the equilibrium back to the left and slowing it down. So there we go with what would happen in case of a temperature increase. Again, it's very important to look at Le Chatelier's principle in terms of energy and say, okay, well, if I had increased the temperature and it was endothermic and I had my kilojoules of energy here next to B, that would have been a very good help into the system. It would have pushed the reaction to the right and helped it reach equilibrium. By actually adding temperature into an exothermic, I've slowed it down and I've shifted it to the left, whereby I'm trying to consume the heat. So again, you need to see if heat is a necessity, as it would be in an endothermic reaction, or if heat is something that is a byproduct and needs to be rid of in a particular reaction, and that would, of course, be the case in an exothermic reaction. So it's important to understand what the disturbance is and in which direction the equilibrium must be shifted in order to offset that disturbance.